Hey everyone, welcome. Thank you for joining us for this paper reading. We've got myself and Duncan here. We're going to go through some really exciting math around reinforcement learning applied to LLMs. We've got a great paper here that covers that. As we talk through this, please drop questions in the chat. We'll be monitoring that. If I can find it in my tabs here. Yep, great. Yeah, so definitely drop questions in the chat, interact with us as we go through this. We love to make this a conversation and interactive. Let's start with some introductions. Hi, I'm Claire Longo. I have a math background, but now I'm working customer success here at Arize, working directly with our customers, which is really fantastic to see what they are all building. And we also have Duncan joining us. Duncan, do you want to give a quick intro?
Yeah. Hi, I'm Duncan. I also work on Claire's team with the customers here at Arize. My background is I've been a software engineer, started out, and then worked in data science for a few years and ML engineering. So I've kind of gone through several different roles, but I'm excited to be here to talk about reinforcement learning with everyone.
Awesome. I'm really excited to have you here on this call, Duncan, because reinforcement learning is something that we've talked about a lot internally. It's personally one of my favorite mathematical models. I'm not sure why. I think it's just so fascinating, the mathematics behind it. And yeah, it's going to be exciting to kind of hear your take on all this. I'm going to go ahead and share screen and we'll show the paper that we're going through, just kind of set the stage here. So the way I like to read papers is I'll go through and mark it up. Some key points really stand out to me. And then Duncan has really pulled out some really important stuff that we're going to talk through with some slides because it's like some pretty in-depth, awesome technical details. But what we're talking through here is reinforcement learning in the era of LLMs. Like I said, reinforcement learning is one of my favorite kind of algorithms here. It's been around for like a long time. I remember learning about it quite a few years ago in school. But now in this era of LLMs, it's becoming more important because it's being applied to LLMs in a way that can really help us apply LLMs to like very specific use cases and kind of keep them on the rails. So what this paper does, and the reason we chose it, is it really gives a little bit of an overview of reinforcement learning in the first place, and then it delves into how to apply it to LLMs in the context of RLHF, which is reinforcement learning human feedback, prompting, and a little bit more. So there were some really cool kind of learnings, takeaways that we got from reading this, thinking about how to apply reinforcement learning to LLMs. And I'm just excited to see like reinforcement learning really starting to catch on in this context. So before we jump over to the slides that go through this main section, I'll just kind of scroll through this and show you what this contains. The first section is kind of Reinforcement Learning 101. You've got some beautiful diagrams that describe it. We're going to talk about online and offline RL. So we actually have some slides that are going to break down these kind of more complex concepts. And then once that's queued up, then we're talking about how to actually apply this in the context of reinforcement learning, human feedback with LLMs. So the thing that really stood out to me here is LLMs, we know they're fantastic. They're large language models. The reinforcement learning helps these large language models adhere to instructions. So when you think about something like, Duncan, you and I were talking about this, a hallucination, maybe you want to talk us through a little bit how that hallucination happens and how we could use something like this to kind of keep that model on the rails and prevent that.
Yeah, so the way that the large language models are trained is more predictive. So they're trying to predict the next token on an individual basis in the sequence. And their feedback mechanism is more based on what you want to hear. Like they're trying to give you something that you want to hear. So if you ask it a question, it wants to give you an answer because that's going to be preferable to like saying that it doesn't understand or it doesn't know something. So it may try and pull together some information to give you a response because that's going to give it better feedback from the person that's judging it. And what we can use reinforcement learning to do is focus the objective of the language model to be more based on providing truthful answers or penalizing answers that aren't that don't have context or aren't based on any background.
Yeah, I love that. I think there's something here. They mentioned a few times like the LM alignment problem. And that like really resonated with me because the LM is a language model. And like you're saying, it's kind of optimized to produce sensible and coherent responses, but not always
Yeah.
accurate. But then when you can layer some kind of objective function around that, I know that's a super mathy term, but like some kind of like mathematically explicit metric that you can optimize for, then you can start to kind of steer these things to do what you actually want beyond just producing helpful language output.
Yeah.
Really cool. Well, Duncan, maybe I'm going to pass it over to you if you want to talk us through the slides, which really go through this first section here, really kind of reinforcement learning 101, the terminology here, and then how we're applying it to the LLMs.
Yeah, let's jump into that. So we're going to go all the way back to the basis of what reinforcement learning is doing. And that's, you can formalize it with this Markov decision process. And the idea here is that the agent in reinforcement learning would be looking at these a system like this, where you have different states that you can be in. You'll start out with like an initial state that could be in chess, that could be like the starting board of the chessboard, where all the pieces are lined up. And then the agent can move from one state to another by choosing actions. So in this, this was actually generated by ChatGPT. I was trying to avoid pulling anything off the internet, but it did a really good job. Like, this is what a Markov decision process looks like. It has these 10 states, and it has 5 actions available that are transition between these states. And then in between, you see these, the numbers are the reward function, or the reward that you get for that transition. So in chess, we could formalize this as like the starting state is the initial board, and then each action is moving a piece. And the reward function in chess, you want the objective to be to reach checkmate. So to motivate that, you could say that like you get a large reward for a state, entering a state that results in checkmate. And then this is like the environment in a Markov decision process is the state and reward, and the decisions are the actions and the transitions between states. Each step, an important part of reinforcement learning is that it's discrete steps. So you're going from a state, you're picking an action, and you're moving to the next state, discrete steps. And then the objective in these processes is actually not to get the maximum reward for each step, but to get the maximum cumulative reward. So that nuance kind of requires some exploration of the space to figure out, you know, if choosing a different action will lead to a better reward in the long run, rather than picking the action at each step that will lead to the largest reward for that step.
That's a really good point there that I want to circle back on. I think the thing that stands out to me with this when you talk me through it is you kind of have like a little bit of a different mathematical description than you would for machine learning. Like machine learning, we're all pretty familiar there, where it's like you got features and you have like some kind of response that you're trying to predict. But here, the definition is quite different, where you really have like states, actions, that reward, and you're really trying to like, the agent is taking steps to do things, and you're trying to maximize that reward. What I really love here is you have that very clear like reward function that you're trying to maximize, and we'll see how that kind of pulls into LLMs. The thing you mentioned here that was really interesting is like you've got your short-term reward and your long-term reward. So like there's actually like some cool parallels, I think, in poker, of course, because that's something I like to think about a lot. But like if you're playing a lot of poker hands, like you can think about like taking actions to maximize like a short-term reward. Like I just want to win this one hand. Or you could step back and look at like your long-term kind of expected value of playing a ton of hands, and you want to actually maximize like your long-term reward there. So having this kind of mathematical framework can really kind of apply to those kinds of like gamified situations there.
Yeah, and it's interesting too that like beyond games, this framework can be made to work for a lot of situations, and we'll go back at the end and show how this actually can be used to with an LLM in training, to improve the actions that it's taking. So it's very generalizable to a lot of different processes, which is really cool.
Yeah.
So then going beyond taking that and taking it to the next step of the actual training of the agent. The agent in reinforcement learning is learning a policy, and that policy is how it approaches decisions in that Markov environment. So like how it goes from one state, what decision it makes to go to the next, that's called the policy. And it's choosing those, it has like a set of actions at each state that it can choose from, and it can move through the environment in that way. So there, to train a reinforcement learning agent, you go through many different cycles of trials where it can go through the whole process. Like for poker, it could play like many different hands or many different hands until you reach like a terminal state. And it'll go through that many times, and it'll learn what actions lead to better outcomes and kind of balance that explore exploit that we talked about earlier. So like in a lot of situations, once it's found a good path for like the first couple steps, it will want to keep that path because it leads to better outcomes in the long run. But every now and then you still wanted to like deviate from that to see if there was a better path in those first couple steps that will lead to like longer term rewards. So there's like a lot of balancing in reinforcement learning when you're training a model between that consistency and like, the first like 10 steps, this looks good, versus like deviating and seeing if you find something better. And then after many trials, the agent learns a policy that can generalize to any state, and then you kind of can let it go off into the wild and interact with the environment. So this
Yeah,
is why we
Duncan,
have these, yeah.
oh, go ahead, sorry.
I was going to say this is why we have these two different paradigms for online and offline reinforcement learning.
Yeah, I love this. You mentioned something interesting on the explore exploit. The explore exploit trade-off here is really why reinforcement learning is one of my favorite algorithms. What this does is it allows the algorithm to constantly try new things and learn from what it's doing. So it's kind of like how we learn as people. Like, I'm going to try something. If it didn't work, I might not do that again. If it did work, I might repeat the behavior. So it is like the way neural nets kind of model the brain. This kind of algorithm is kind of modeling how humans learn. The thing that makes this so powerful, I think, is like when the model is learning, you're optimizing the kind of optimal happy path that you've learned, like what's maximizing reward. You're going to start to like do that behavior a lot, but then on the side, you're also going to continue to explore. So you don't just converge to that one kind of happy path that you found, because maybe the environment's changing and you need to update your happy path, or maybe that happy path is kind of a local minima and you're kind of stuck somewhere that's like good but not the best. And so by being able to like randomly explore a little bit of percentage of the actions that you're taking, maybe random or following some kind of like different policy other than the optimal one, that helps us like get new data and adapt to what we're seeing, which is really what I think makes these things so powerful.
Yeah, I think that's a really good point about the local minima. That it's very robust to those types of things. Like it can get out of a local minima pretty better than a lot of like gradient descent type algorithms.
I love that. Often I feel like I, as a human, am stuck in a local minima. So
Hmm.
it's a great parallel.
So like the difference between these two online and offline paradigms is kind of subtle. So like with the online reinforcement learning, we're saying that the agent can interact directly with the environment. And this is usually seen in situations where it's like a video game. You can release the agent into the video game, let it, run the controls based off of the screen, and you're not too worried that it's going to run into issues doing that because the environment is kind of isolated. And then offline reinforcement learning is more common in like the industry because you're not allowed to interact with the environment. So like if you're training a self-driving car, you're not going to put an agent behind the wheel of a car and just like tell it to learn how to drive. So you have to develop like an offline decision data set to teach the agent how to interact with the environment through like a simulation without ever interacting with the environment. And once it's trained, you can use that behavior policy to make decisions on the real environment.
Yeah, I think
So
that's
then,
there.
yeah. the next thing that the paper goes through is some of the actual paradigms of reinforcement learning to kind of drive towards um, the reinforcement learning from human feedback. And to get there, we have to talk about things like imitation learning. And this is a different approach to reinforcement learning, like the offline reinforcement learning problem, um, where the agent can't interact with the environment. So we need to have some kind of way of teaching it what to do when it's in the real environment without exposing it to that environment. Um, and it's so the explanation here, like the need to, and it's also the other piece of it is that like when you're teaching an agent to drive, it's not very clear what the rewards are, what the reward mechanism should be for driving. So it's hard to come up with a reward function to teach the agent which actions to choose when it gets information from the state. It's not necessarily clear, like, or if you're training an agent to pick something up, like you can give it a reward when it picks it up, but how do you get it there? It's hard to tune a reward function. So in imitation learning, instead of doing that, you have like a human driving and you use that data set to teach the agent what expert decisions are being taken. So in this example, like the a human driver, like an expert, goes through the same course that the agent is exposed to and makes decisions. And then the agent has access to those decisions and uses those to build its own policy. So it sees what a human is doing and then it says, oh, I should build a policy that's similar to that. And that's the imitation aspect.
So in this case, it's kind of learning from example.
Yeah, exactly.
When you think through
Um,
this one thing that kind of tripped me up here was like, how is this different from like machine learning where we train offline with like example data set? What's kind of your thoughts on that?
yeah, that's a good question. I think that like with this mechanism, the agent still has a little bit of leeway to like explore. So it can try other actions and see how
Yeah.
that, because it's still passing that action to the environment. It doesn't need to go off of like totally imitate everything. Um, so there's still some aspect of that explore exploit, but for the most part, it's like it's most of its information is still coming from the driver. So it wants to stay close to that. So it gives it kind of a head start, is the way that I think the paper describes it. You're giving it a head start so that it has something to go off of, and then it can build its policy through more exploration once it has the basics down.
Oh, that makes so much sense because it's still defined as like a reinforcement learning problem. So you still have that explore exploit mathematically there. That makes a lot of sense. And then there's something in the paper here about when it's difficult to define the policy or the reward function, this can allow it to kind of learn that. Am I thinking about that right?
Yeah. So I heard an example about this where from a book called The Alignment Problem that was talking about alignment and reinforcement, where you're trying to align the the way that the rewards are designed with the actual behavior that you want to see, which is actually a pretty hard problem. Like if you want,
Yeah.
uh, there's a lot of ways that you can create a reward function that lead to outcomes that you wouldn't want. Like, you know, you could train a model that you get a reward in chess every time you take a piece based off of the value of that piece. But that doesn't necessarily lead to checkmate. You could still lose the game pretty easily if you just are basing your reward off of capturing pieces. So the 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 problem in the book was learning to fly like a model plane and do like loops and different like aerial maneuvers. And it's really hard to even get the an agent to learn how to like take off a plane. So they going off of that problem, they tried to build reward functions for it and couldn't do it. And eventually they came to the conclusion that if the only way to get the agent to the level that they needed to get it to was to show it like sensor data from a human flying that plane and show it what they wanted it to do up to that point, and then eventually the agent learned to like execute these maneuvers far better than the human could, which is
Yeah, that's
interesting.
actually super powerful framework there because you're leveraging both learning from example as well as optimizing that reward function with explore exploit. Alignment problem. What a great title for a book because that's kind of like the issue with LLMs today is like that alignment problem. That's how we're kind of applying the RL here.
Yeah, Yeah, it was before LLMs, but it's definitely ahead of like kind of ahead of its time.
I'm gonna pick that book up. I love that.
So the kind of the next logical step from imitation learning is this idea of inverse reinforcement learning, which isn't that it's a the author talks about it as a type of imitation learning. But it works in two steps, where instead of basing all of the agent's decisions, training it off of a decision data set from an expert, you're training the reward model as like a standard machine learning problem to give rewards based off of the decision data set. So you're trying to figure out what rewards would have incentive, like you could think of it as what rewards would have incentivized that human to execute those behaviors, and how do you capture that in a like reward model. So as somebody's driving, they like take a left turn to get to the street that they want to and stay within the lines. The reward function is looking at like what incentives were driving the human to make that decision, and like try and capture that. Like if they were trying to stay in the lines, they were trying to go to this street, to stay on their path, those types of things. So like it's training the reward model and then using that reward model to train the agent directly.
Interesting. Whereas like the more traditional machine learning model or I'm sorry, not machine learning, traditional like RL model, is actually optimizing directly the actions to drive the reward.
Yeah, it's so in the imitation learning, it's basing all of the actions off of the human behavior, and then the agent is kind of just learning a policy um, that continues with those actions. So this is done in two steps, where you have to first build that reward model. So you take take the same data set that you were training the model on with imitation learning, and you use that to train the reward model instead. And then in the second step, you can use that reward model to train the agent.
That's pretty cool.
And this is kind of more like the paradigm that's used in reinforcement learning with human feedback, that we'll talk about a little bit later, which is why we had to go through all these steps to get here too. And that's the next thing that comes up is, um, and this is the way that it's formalized in the paper, is that a human demonstrator takes these prompts that people are putting into that would be putting into a large language model, and demonstrates the output behavior. So like that's the decision data set where a human driver would be driving to show the model what to do. And this is used to do fine tuning. And
Yeah,
then
it
in the
stood
second
out to
step,
me here that they're doing the fine tuning, like that's part of this workflow here.
yeah, because we hear about it a lot, but it's kind of hard to see how it fits into the overall process.
Mhm.
So in the second step, it's collecting data. So more prompts, like a large set of prompts to sample from, and using those to have the labeler rank the best to the worst prompts. And this gives the agent some feedback to go off of. And that's used to train the actual reward model. So the agent is learning what the human thinks is better or worse in terms of its outputs, so that it can, so that that's actually just the reward model. So it uses that to decide, in the overall reinforcement learning problem. And then it optimizes a policy to output data that gets the highest reward.
Yeah, so that's where you're mathematically defining what you want this LLM to do. So if you don't want it to hallucinate with this reward model and the policy that you're optimizing towards, you've defined it mathematically, and you're kind of like forcing the system onto those rails mathematically, and it's going to converge to the right place over time. So if your model's doing something you don't want it to do, like hallucinate, you're kind of protecting it against doing that and teaching it not to do that, I think is the right way to do that. Right way to say it, but you've got this mathematical way of doing it. So instead of just like saying in a prompt, which I see a lot of people doing today, and I think it can be quite effective, like you can give like very explicit instructions in a prompt, but like sometimes it's still going to generate maybe something that's wrong. And this is going to kind of like pull it back to keep it on the rails for what you want it to do.
Yeah. And it's interesting that you talk about the prompts because like you're going off of this data set where it's sampling a lot of prompts and you get the control, somebody gets the control over what the ranking is for those outputs that the model's producing. Um, so like your control mechanism goes from like having to write some kind of reward function or having to write some kind of prompt and hoping that that does the job um, to like, so it's a different framing of that alignment problem that you're talking about. Like you're trying to align the model with a prompt change or like to adjust how you're what you're telling it to do. You could also adjust it by writing a reward function for this directly and saying like explicitly, this is how I want the model to behave. But that's a much harder problem to generalize across every prompt that it could get. So instead, you're controlling like your feedback to the on the prompts and saying like this is a good prompt, this is a bad prompt, and then just trusting that a reward model will capture that and use that to tell the agent what to do.
Yeah, that makes sense. What are like some examples? I was trying to think through some examples here of like what is an example of the reward and a policy for like a real life application? Like I think sometimes about generating marketing content and I want to optimize some kind of like true metric there. Like I want people to click on the email I send or I want people to purchase the item. So you have a metric there.
Mm-hmm.
Um, does that feed into like the reward model here?
Yeah. So in that situation, like if you were sending out emails and you were looking at the response rate as like the feedback, you could you could train a model on the email and the response rate and use that as the reward model to kind of direct the behavior to produce more emails that look like the input.
Yeah, that makes sense.
And then like so like that reward model would take in the output of the model and then give it a reward score based off of the expected clicks.
Mhm. Yep, I love being able to tie it directly to a business metric.
Yeah, it's interesting that um, I hadn't thought about like actually formalizing it in that way, but yeah,
Yeah, it could
it kind
be.
of helps make it click a little bit.
Yeah,
And
honestly,
so
the
this,
slide you're showing earlier is where it kind of clicked for me because I've always thought about like reinforcement learning human feedback, but I'd never seen like a diagram of like what that workflow actually looked like. And it was kind of an aha moment to see like those steps that you just laid out.
yeah, I agree. Like this slide was really, or this part of the paper was so powerful to me that I just pulled it out into the slide because I thought it was really
Yeah.
interesting. It helped me understand how this is applied to actual language models. Um, and so basically what it's saying here is that going all the way back to the first slide to the Markov decision process means formalizing how this works. So the initial state pulled from all possible states is the prompt to the model. So that means that the states for this are just concatenations of strings, like like concatenations of tokens. That's your state. So when you're in a state in when you're training this reinforcement learning for human feedback, that's the text, either the response or the prompt. Um, and so the action based off of that initial state of that prompt is to pick a new token. And that's the first token of your response. Um, and then you concatenate that to get the next state in the transition. Uh, and then you get some kind of reward for that based off of the reward model that you've trained. And then you keep going. So it's like each state is just the prompt and the next token and the action that you've chosen, which is the token also. And then your action is to pick the next token. So you're just picking one token after another, which is actually how LLMs work. Um, so this really, I thought, was a good way to like formalize it. And this goes through what that means in terms of the MDP. These are the parts of the MDP that we have. Um, and then the last thing that I want to bring up is that, we talked about in the last slide how the model learns from human scoring But it seems like you could also do the same thing with an eval, like another model that's judging the responses.
Mm-hmm.
So you could write an eval to say, like, I want a response that looks like this, and use that to develop a reward model instead.
Oh, that's powerful because that's one of the common ways that people will actually measure the performance of an LLM in production is the LLM eval. It's essentially functioning as like LLM as a judge. So you have one LLM model evaluating the output of another one. And it's a great way to just like generate a metric that you can actually track to see like, hey, is my system going off the rails here? Is it hallucinating? And yeah, so you actually have like a prompt in the loop there that is doing the evaluation.
Yeah. And so that kind of makes it a closed system where you don't need it. You don't actually need the human because you can have the LLM evaluate or a separate prompt evaluate the response at each step.
Yeah. When you and I read this, we both kind of had the same takeaway. I think we were both surprised that it is at the token level. So like the action is the next token, that's the next word to be generated in the output. And the state is like concatenation of all the tokens. That's so interesting because that means we're actually optimizing this at the token level. And my assumption before I read the paper, it's a good thing I read it, was my assumption was that this was maybe optimizing things at a level where it's maybe like this prompt versus that prompt, where those would be the action. So it's kind of an interesting takeaway here.
Yeah. Thank you. So that's the last slide. I think it's good to jump over the paper and talk about that a little bit more because I think
Let's
it
do
goes
it.
through some of that.
Yeah, let me share the paper here.
Because what you were talking about with this one, the output in this like in this formalization
Yeah.
is a token. And that's the next section in the paper, I think, is that he talks about how we actually don't have access to the tokens. So in an ideal world, we would be judging each token would get its own reward. And that would give the agent more information to go off of as it's developing the full response.
Yeah.
But
But in the
instead,
real
we
world, what do we have access to there? Like, what is the optimization done on?
think it's
Where are we looking? Is it credit assignment?
credit assignment. Yeah.
Yeah. Okay. Yeah, so here they're talking about the credit assignment. The learned reward model can only compare responses on an entire level. So they're concatenating everything up. So they're actually is a way to assign credit to different tokens or part of tokens. Yeah. Okay, that's interesting.
Yeah. So he talks about how dense reward problems are easier to learn. So like you want to be giving feedback at every step that the agent takes. And in this case, the agent is choosing each of those tokens sequentially. And it would be able to learn faster if it had like if it could explore within that space of choosing tokens which ones are going to get a better reward overall. But
Mm.
instead we get the full response and have to just give it a single reward at the end. And it doesn't get to
Oh,
choose a bunch of
interesting. So the reward is actually not assigned at the token level. It's actually like you're creating the state and the action by concatenating tokens up until a certain point. But then the credit assignment, that like reward optimization, is still happening based on the action level, which is like a concatenation of all your tokens up into that date.
Yeah, so maybe OpenAI could do that with access to the underlying model.
Yeah. Okay. So you need access to the underlying model to really optimize this at the token level.
Yeah.
That's really interesting. The other thing that stood out to me actually was prompting. So the actions that are taken to improve the system is fine tuning. So there's kind of that loop up in this really cool diagram here where you're using this data to fine tune with ChatGPT. It would be interesting, I think, to think about how to optimize the prompting strategy under this, because kind of under this framework, because worked a lot with LLMs. I've prompted them quite a few times, and I'm really starting to notice that the way I prompt really matters. Just like the articulation and use of language, because it is a language model, matters. How you're really instructing the system. So when I'm iterating and building an LLM system, I am iterating on my prompting strategy quite a bit. And that would be something very interesting to kind of mimic here.
Yeah, I think that.
Oh, we got a question here. I wonder if there is a response to it. I wonder if there is a method to deconstruct the response and measure delta between request, prompt, and response at the token level. Hmm.
Yeah, I think that's a good idea. So are you saying like pulling apart the tokens that are in the response and looking at that like separately, individually? Yeah. Yeah, I think that that's an interesting idea. If you could feed that back into the model somehow, um, and use that to develop the policy, I think that that's interesting.
That would
Yeah.
be interesting. Yeah. It could be mathematically measurable, maybe with like a maybe cosine similarity, not my favorite one, but Euclidean distance, because you could get that embedding representation of the data there too.
Hmm.
Yeah, good
Yeah,
question.
and then also like adjusting the prompt too, like at the same time, if there was a mechanism to get that, yeah, to improve that.
Yeah, I think they have a cool example here actually of the prompt and what optimization there could look like. So you kind of have like user inputs, asking a math question. TBD if I think that's the right thing to do with an LLM, but I always like testing their limits here. So we're asking what's a raised to the power of 4 equals 1. What is a? It gives a correct answer. That's great. And then this prompt here, we're saying the prompt is a little bit different. A raised to the power of 4 equals 1. What is a? Two experts are debating on the answer. And that is like often a good way to get to prompt engineer to like get these systems to reason and then give you the right output. But in this case, it gives a wrong answer. So this is such a great example of like comparing two prompts. And you could start to converge on which one is giving you correct answers here if this was kind of more dynamic.
Hmm. Yeah, it's a hard problem. Yeah, it goes through, I think those next couple of sections, I didn't go as deep into these, but it seems like it goes through that prompt optimization. And if you could um, like use prompt offline reinforcement learning to optimize. Um,
Yeah, it looks like they're talking about it right here. You definitely use like an offline data set here.
mhm.
Yeah, I know we're running close to time here, but overall my takeaway on this paper was like I loved it. The math was really fun to read through here. I really liked that it gave me like the overview of reinforcement learning before it helped us think through how the reinforcement learning is actually applied in the context of an LLM. So it really helped me kind of map what I know about reinforcement learning to that context of the LLM. And for me, like that really was the aha moment when I think through kind of this workflow here and seeing how that flows. And then when they break it down with these diagrams, you can just kind of see like, well, I know what a state is, I know what an action is, environment. How does that actually map to the reinforcement learning or I'm sorry, the LLM world? I'm getting my
Mhm.
models mixed up, but yeah, how does the RL map to the LLM world? And they really made that mapping really explicit here and also laid out some great kind of next steps here with the um, credit assignment and prompting as well. Duncan, what's your kind of high level takeaway here?
Yeah, I think that yeah, like I was really excited about like this the last thing that we specifically talked about, the credit assignment, because it seems like that is a better like first with their formalization of like picking the next token as the action and then getting feedback at that level, then the agent has a lot of different paths to take, even just with responding to a single prompt. You know, so like you could train on the same prompt. So in their formalization, you're sampling, you're picking a prompt from like a set of prompts and running the model on it and getting a reward off of different responses. But you could take the same prompt and keep doing it over and over again and adjusting the path that you take through selecting from all of the tokens, because all of those tokens are the actions that you have access to. Um, so yeah, it's just like gets a little bit deeper into the weeds there.
We got one question from the chat here. Well, two. Eric recommends that we look up DSPY for prompt optimization. So I'm definitely going to check that out. It's a cool problem to solve. Matt asks a great question here. So if I, a model, assuming I'm a model, force a user to provide feedback before giving them a new answer, I can continuously learn from users and adjust my weights, add parameters. Would this be a good example of RL in practice? I think somewhat, but I think you would actually want to, let's see, so you force a user to provide feedback. So you got that user feedback, right? And then you're giving the right answer. So you've got the user feedback and the answer there, and you can continuously adjust. I think like kind of the reinforcement learning, like a good example of that in practice would be like a model is getting human feedback, like feedback from the user. And then based on that feedback, you are adjusting those weights, parameters, that kind of thing in your mathematical definition of like policy and reward. So you don't really have to like not give them the answer. You're just like, you are getting that answer through the feedback loop and then like adjusting from that, I think is kind of how I think about it. But Duncan, how does that really resonate with your understanding as well?
Yeah, I think that this could be a way to like set up a like reinforcement learning um, system where you're so like for example, like we see every day, like with ChatGPT, it has like the response, like is this a good response, is this a bad response, or even just like with text feedback. They can collect that information and use that to train a reward model. Um,
Yeah, exactly. That's kind of the signal you want to grab.
yeah,
Johnny Lynn makes a great point here. Won't it forget things if they concatenate and truncate words at the token level? It would seem to be limited by the token limit. Yeah, right? Because like, isn't it kind of similar just having like a super long prompt or like a really long, like if you're in that search and retrieval and you retrieve like a ton of documents, sometimes too much information into this thing and it know how to pinpoint the right information. So if you have like a very long document in any of those contexts, I think you do have that challenge.
yeah, yeah. It's like probably even more of a challenge than with the training the language model, because your context is like includes the prompt at every step. So it's yeah, it is that is probably a problem.
Yeah, I think that's a good problem to kind of solve there. Raymond says latency though. Yeah, I mean, isn't that kind of the known thing with reinforcement learning is latency challenges? I do like the offline learning and kind of like learning from example before the thing goes live. I think that probably helps jumpstart it, but that is a challenge that I've heard before with reinforcement learning. And when you got the human in the loop, like you've got to wait for the actual real human to like come up with the feedback and get back to you. So that kind of adds to it. Yeah. One thing that actually stood out to me is the human in the loop here. Because one assumption I had before I read the paper, where's our lovely diagram? Before I read the paper, I thought like you could maybe put like an automated feedback loop here. Like signal that's generated automatically. I guess a human has to generate it, but like a purchase or a click, those kinds of signals are usually generated automatically through your software where this thing is getting deployed. And so you might not need like an actual human labeler that's like got the job of like actually reviewing things. It might be a little bit more automatic here.
Yeah. And I think, yeah, we talked about the evals too. Like you could use an eval to judge the responses based off of some criteria that you put. It also kind of like I feel like every time you throw something into an LLM, it adds ambiguity in terms of what it's doing and if it's, picking up the right signals. But you kind of have the same problem with the human labeler.
Yeah, that's a good point. Cool. I think we're right at time. big thank you to the community for the questions. I love making this a conversation. Thanks for joining us today, guys.
Yeah, thanks everyone. Good questions.
Bye, everyone.